Alright, areas of regular polygons. What could be more fun? I can't think. Okay, it's about finding the area of a regular polygon. What's a regular polygon? Regular polygons are polygons, and I've already drawn some here in circles, that are all the same sides and they have all the same angles. You can kind of tell already how we're going to try to find the areas of those in general, because each one of those you could draw a circle right around. You could inscribe it in a circle. You could draw a circle that just goes on the outside. Actually, you could inscribe a circle too, but finding the area is going to be easier if we do it this way. And actually, eventually, this is going to help us with how we find the area of a circle, because you notice as we get more and more sides on the thing, it gets closer and closer to the actual circle area. But more on that later. For now, it's how do you find the area in the first place of the regular polygon? Well, yeah, a good idea is to put it in a circle, and then there will be a center. If you can put it in a circle, that center of that circle we also call the center of the polygon. And from that center of the polygon, you can draw these segments that go out to the corners. And those, actually, they call that a radius. They call that a radius of the polygon in this book. I don't think every book calls it that. It's the radius of the circle. That's also called the radius of the polygon, which I think is kind of crazy. But the one that's probably the most important, oh, central angle. Central angle, you know what, let me just go to the Sketchpad version of this. The central angle is this thing here. Oh, by the way, let me show you this. Isn't this cool? I made this. I learned how to do this from the dude at the conference. I can just hit plus or minus and it adds to the number of sides. I made this from scratch. I'm so happy, but I didn't make enough sides. If I keep adding sides, I start to lose some. Anyway, yeah, the what was I getting at? I got off track. The radius is this thing here. This thing here is called the apothem. It's this. You know, if I make fewer sides, it might be easier to see. It's this segment from the midpoint to the center of the circle. It's kind of like each one of these triangles has to be isosceles, of course, because it's a regular polygon. But if I want to find the area of that triangle, I need to know the height of that triangle. I need to know the length of the segment that's perpendicular here, like this thing. You can kind of think of it like an inner radius. It's like it would be the radius if there was a circle on the inside. Ooh, I could actually show you that. If I made a circle like this, it would snap right on there, and it would be actually the radius of the circle that's just tangent to all those. Oh, my phone's ringing. I'll be right back. Okay, so that's apothem. It's that thing in there. So, and as we add more and more sides, you notice the apothem and that other radius start to look really almost the same length. And I can add a bunch of sides even though the thing isn't complete. But this starts to look a lot like the actual radius of the circle. Okay, keep getting interrupted. That's probably good because this is probably going to go on forever. And the fact that the apothem is starting to look a lot like the radius when you get really big, when you get really small values here, now the apothem and the radius are very different. But in any of these cases, I'm going to want to be able to find these triangles. I'm trying to get one that doesn't look like something you've seen before. Okay, this is kind of a weird one. I can find this if I know this because there's always a right triangle here. I've always got isosceles here because these are radii of a circle and of the regular polygon. I've got all kinds of trig I can apply here. So if I knew this, if I knew the length of the side, the number of sides, actually, that's all I need to know. Because with the number of sides, I can figure out what this angle is supposed to be. Here with 7 sides, I know that the central angle in here is got to be exactly 360 divided by 7. If you think about it, all these angles meet at the center, they go all the way around the circle, and there's one of these triangles for every side there is. So the length of, the size of this angle is always going to be 360 divided by 7. So the size of this angle in here, whoa, why did I do that? The size of this angle in here is going to be half of that. So take that and divide it by 2 for the one that's in the right triangle. So if I knew this length, I divided by 2, I could find this area of this triangle pretty easily. But that's not how the formula starts off. The formula starts off basically if you knew the perimeter of the thing. If you knew the perimeter of the thing, or if you knew the apothem, it would be really easy to find the area of all those triangles added up. It's actually half times the apothem times the perimeter of the whole polygon. Perimeter of the whole polygon is really the sum of all these little bases. So it's kind of like half base times height, where the base is one of these things. The height of the triangle is the apothem, you can see there. And but if I add up a bunch of those, the bases actually kind of combine, and really what I'm talking about is the whole perimeter. So really the area of the whole polygon is just half AP, half times apothem times perimeter. I got lots of time left. Let's go ahead and do some of these examples. Oh, did I show you this yet? This is the questions you're going to have to answer at the beginning of class. I'll give you a second to look at those. Okay, so then let's go to it. Let's do some actual examples. Here's that septagon again, and let's say you're trying to find the area, and in general, you know that area is supposed to equal a half times apothem times perimeter. Now, the easiest way you could get these, the most straightforward way, is if someone actually gave you the apothem. Straight line, yep. So actually gave you the apothem and gave you one of the side lengths. Now I got to be careful. If I make up a side length here, it could actually not be a regular polygon. So I'm not going to be that nice. I'm going to say, okay, that's all I'm going to give you. I'm just going to give you the apothem, and you got to find the area. Okay, well, if that's the apothem, here's my task. I got to figure out the area of one of these little triangles. One of these little triangles, this is starting to look really bad. Let me fix this a bit. I give you that the apothem was 10. So let's actually draw a nice apothem. Let's draw a nice radius. Let's realize that, yes, we are trying to find the area of this thing. This is 10. It's the right angle. I know there's 7 sides. That's enough. It'll tell me I can find the area. First of all, let's figure out the angle of this little piece right here. If you think about how many right triangles this whole thing is divided into, I have really 7 big isosceles triangles, but then each isosceles triangle is divided in half to make a right triangle. So actually there's really 14 of those little right triangles. It's kind of like, you know, half of one of these things. There's 14 little right triangles in the whole picture. I take 14 of these little angles. Before I said 360 divided by 7 divided by 2, but really you could actually just say 360 by 14 is that. Sorry if that's a little bit confusing. 360 divided by 14 is the same as 360 divided by 7 divided by 2. That central angle of the little right triangle is 25.7 degrees. So I need to know that because I don't know anything about the length of these sides. I'm supposed to know the perimeter. I don't know the perimeter if I don't know the length of the side. The only thing I gave you was the 10. Knowing that this is a 25.7, I can use some fancy trig now. I know the side adjacent to the 25.7. I'm looking for the side opposite to the 25.7. So I'll say opposite and adjacent, that's tangent. Tangent of 25.7 equals opposite, I'll call it x for now, over adjacent. So I need to find 10 times the tangent of the answer I just had, which would be 4.81. Oh, 4.815. So that means each one of these little guys is 4.82. The perimeter of the whole septagon is 14 of those because that's half of a side. So perimeter, that means perimeter equals 14 of those. I get 67.42. So the area of the whole thing equals half times apothem times perimeter, which is 337. And that's pretty amazing. I mean, all we had to start with was the apothem and the number of sides. I was able to find the area. Okay, so here's a different type of problem. Here, instead of trying to look for the perimeter, I'm going to give you the perimeter. I know the area that I'm looking for is a half times the apothem times the perimeter, but the only thing I know is the perimeter and the fact that it's a pentagon. That's huge. The fact that it's a pentagon, I know how many sides there are. I can hope to find angles at the center because I know how many there are. Here, that's a half times a times 75. The fact that it's a pentagon and the perimeter 75 tells me that each one of these sides has to be 15. I just took 75 divided by 5, and I get, divided by 5. And I get that each side has to be 15. Great. When I make an angle here, I know this part in here has to be 360 divided by 5. It's 360 all the way around this point at the center. There's 5 little wedges coming out. And if I divide 360 by 5, I get 108. Oh, sorry, 72. You'll see why I said 108 in a second. That's not approximately. That's exactly 72. So that little angle is 72, which means if I was going to ever want to make a right triangle at one of these places where I cut this in half, the angle at the top of the right triangle would, if this whole angle is 72, this is going to be 36. And I know if I'm cutting this in half, I know what this is. That's 7.5. What I'm interested to find out is this apothem. If this is a 36-degree angle, remember I have to do this because if I'm going to use trig, I have to be talking about right triangles. So now I'm in a right triangle. I can't use it here. It's not helpful. The A here is adjacent. So that's helpful because A is also standing for adjacent, but it's the apothem adjacent to 36, and the side opposite is 7.5. You notice we're using tangent a lot lately. Tangent of 36 equals opposite over adjacent. That means adjacent or apothem is 7.5 divided by the tangent. We've done that a lot. You know, it's kind of been a while since we've done this. Hey, I used to think this was an easy chapter. That looks pretty difficult. All right, 7.5 divided by the tangent of 36. I get 10 point something. And you should look back at these and go, yeah, does that look reasonable? I mean, is it supposed to be bigger than 7.5? Yeah, I think it is, so, you know, but not horribly bigger, so yeah, that's fine. So, apothem, I'm done. I just put that in here. This is, whoops. This is a half times apothem times perimeter. And if I do that correctly, it's still in my calculator, I just go times 75 divided by 2, I get 387. The area of this pentagon. And again, looking back to the beginning of this problem, I think it's a pretty amazing accomplishment that we were just talking about. If all I knew was that it was a perimeter and it was a regular pentagon, I can actually find area from that. Well, in the name of not filling up 15 minutes just to fill up 15 minutes, I'm actually going to stop here. I'll go back and show you those questions you're supposed to have at the beginning. I think this is kind of hard, but I've done one that's about the same. By the end of the chapter in the book, the problems are getting you to generalize. If you knew the angle, how do you find the number of sides? Or if you know the number of sides, how do you find the area using n to find the angle in the formula? It's great stuff. Headed to our way to find areas of circles. But I'm going to stop here. I will see you in class.